Started. So welcome everyone to this QCIT/Quantum Center colloquium hosted by ETH Zurich. It's my great pleasure to welcome today Chris Monroe, who's a professor at Duke University and also the co-founder and chief scientist of IonQ, a large quantum computing company these days with trapped ions. And I'm very pleased that Chris will tell us a little bit about the most recent results that he had in quantum simulation and quantum computing with trapped ions. But let me also, for those who don't know Chris very well, say a few words to his background. Chris did his PhD, I think, at the University of Colorado, is that right? And then worked in the lab of Dave Wineland. And if many of you have heard the story of 1995 and then Shor's algorithm, quantum gates, suddenly quantum computing became a real thing. So Chris was actually part to co-lead the team that made the first quantum gate happen. So that was at NIST. And he then moved to the University of Maryland, where he set up his own lab, his own group, and pioneered teleportation experiments. So he was the first to entangle two separate ion traps, so the ions in two separate traps optically through an optical interconnect. It was one of those milestones, and has since then moved to the University of Maryland, where his group grew and also the number of ions in the trap grew. So Chris has then pioneered lots of quantum simulations of magnetism, phase transitions, and all kinds of interesting physics phenomena on the one side with many, many more ions, and on the other, quantum computers. So how do we run quantum gates? How do we make scalable quantum computers? And that also led to the spin-out company, I guess is the right term, IonQ, that he co-founded, that's now making commercial quantum computers. But with that as a background, let's just jump in straight away. So please, Chris, take it away.
Okay, thank you.
Oh, and one more thing. Sorry, yes. If you could write questions, if anyone has questions, feel free to drop them in the chat and I'll ask them. Or if we have enough room, then I will also unmute you so you can ask your question that way. Take it away, Chris.
Okay, thanks. Thanks, Cornelius. It's a great pleasure to be here among all my friends at ETH. I only wish I could have been there in person, which was originally the plan, but other things got in the way. So I'm very happy to actually give, I guess, two presentations today and also tomorrow as ETH has a symposium launching or kind of celebrating their own quantum center. So I look forward to talking tomorrow a little more on the IonQ side and a little bit about what the quantum business world is like. And I see Nicholas Gizan is there. He was one of the first to ever really do that. So anyway, I look forward to sharing some stories tomorrow. Today, I'll spend a little more time on the research side at the universities. And yes, I'm like Cornelius in the middle of a move to Duke University. I'll tell you a little bit more about what we have in store down here. Of course, I'm joining my longtime colleague, Jungsang Kim at Duke, and he and I are the co-founders of this company, IonQ. But today I'm going to be a little more general and talk about given this seminar series, I presume most folks are up to speed with qubits and the opportunities therein for information processing, communication, and so forth. I'll be concentrating today on computing and simulation, which I look at as pretty much the same thing. A quantum simulator is a more restrictive version of a quantum computer, if you will. And it's interesting to have these philosophical arguments of definition, which seem to be prevalent in quantum pretty much at all levels. But a quantum simulator, it does need some kind of control. You have to be able to tune certain things. And a quantum computer, of course, gives you full control, universal control of any quantum system. And here the philosophy comes from this. If I give you a single hydrogen atom, it's actually very hard to compute any pair of energy levels, the separation of the two energy levels to say 20 digits. It's very hard to compute it. It can be done up to many digits. And you might ask, well, is the hydrogen atom doing a quantum computation for you? And or even a quantum simulation? Well, it's simulating itself, I guess. So it's a little bit of a tautology. But to me, what's lacking is the control. The hydrogen atom is given to us. We can't really tune it. We can't play around with it. So it lacks the the number of controls that we would call it a simulator. So I'm going to talk about both of these sort of in the same breath, computing and simulation. But in the system that I will present, we have a great deal of control. Maybe not universal control in certain cases, but a great deal of control. So I want to step back a little bit, though, and talk about hardware, what you need to build a controllable quantum system. And if you're thinking about a computer, it's natural to think about how conventional computers are built from solid state devices, transistors, and so forth that latch naturally. I want to show just a high level slide that this is a line I share from my colleague Bill Phillips at NIST in Gaithersburg and at University of Maryland. And he's fond of saying that a quantum computer differs more from a laptop than that laptop differs from an abacus. And what he means here is that the laptop and the abacus are both Turing machines. They're both classical Turing machines, even though one is a lot faster, a lot more useful. But the basic physics of computing, if you want to call it physics, the basic idea of computing is the same thing. And there's this abstract model of a Turing machine that has, a memory element and a tape that can move around with the memory element, and you can reduce any classical computation to that Turing machine. The thing is about quantum computing is it's not a Turing machine. It's a totally different model of computing. And so I think the corollary to this statement here on this slide is that why should we think that a quantum computer will look anything like the classical computer? So when we think about building quantum computing devices or quantum simulators, we have exotic systems that are super well isolated. That's the main requirement for a quantum system, that it's not observed, that it doesn't have a uncontrolled interaction with the environment until you're ready to read it out. And then you need to have a very strong interaction with the environment. So being able to gate the environment is really tricky. So I tend to group the technologies into two camps: one, synthetic qubits, and two, natural qubits. The synthetic qubits are, again, a little bit like trying to refine silicon to do quantum. So they're typically based in solid state. And what's remarkable, of course, is that there are emergent degrees of freedom in solid state systems like superconducting circuits. When you get them very cold, of course, the current can flow without loss. And there's your isolation in a way. There's very little interaction. And the ability to print out superconducting circuit elements and wire them together is pretty clear, a kind of big gain to think about building a quantum device. I think some of these other technologies are quite a bit far behind. I think enforcing silicon itself, say the spins, to behave quantum mechanically is really hard, even though there's so much technology behind the fabrication of silicon. The most beautiful physics idea is probably a topological qubit, where there may be a material that sort of naturally error corrects and naturally latches. Although, again, it's beautiful physics, but in terms of devices, I think everybody would agree that we're not even close to even seeing that type of behavior. And there are, some interesting optically active quantum systems like color centers. NV diamond is a very popular one, maybe more for sensing of proximal magnetic fields. But I'm obviously going to concentrate on trapped atomic ions, which is where my specialty lies. But they're one of the, I would argue, they're the leading form of natural qubits. That is, the quantum systems are not manufactured at all; they're given to us, like atoms, ions, electrons, individual photons. Doesn't mean it's trivial. In fact, it's very hard. What we have to do is control them. We have to typically trap them in a vacuum chamber so that they don't interact with air and other things. Photons are interesting, of course, because you can send them through waveguides and air, even with very little interaction, but they also lack a memory. And there's not a very good history of all photonic computing, even classical computing. So it's thought that that massive natural qubits like atoms are one of the leading candidates. And so I'm going to dive a little more into that and talk about trapped atomic ions. One thing I've learned at IonQ is that you have to say this many times to investors and so forth that are used to silicon, and that is, this is exotic stuff, trapping individual atoms, but there are no manufacturing errors. The atoms are all exactly the same because they're atomic clocks. In fact, these are the qubits that we use in atomic ion quantum computers are very much like, in fact, they're pretty decent atomic clocks, so therefore they can be replicated with near perfection. And that's a big deal when you're thinking about scaling. So here's a picture of a bunch of ions on an ion trap. So here we have exactly 80 ytterbium ions. Each dot is a single atom. I'm sure at ETH you've seen pictures like this before. There's a wonderful, vibrant ion trap group there led by Jonathan Holm. And now Cornelius is joined, and ETH is, they're already a powerhouse in this field, but it's very exciting to see that. So these atoms are separated by a few microns, maybe about 5 microns. They're glowing because we're shining laser light that's resonant with transition in the atom. And of course, this picture has been expanded and inserted with a picture of the trap that's holding it. The trap itself is a chunk of silicon. That sounds pretty simple saying it that way. This is made by Sandia National Labs. It's a very complex thing, but there's nothing quantum about it. This is just a host of a bunch of electrodes. If you look closely, you might be able to see a few of them. There's about 100 electrodes in this linear trap, and the ions actually float above the surface by about 1/10 of a millimeter. And this is a centimeter on a side, by the way. So they're just floating above that surface there. And they occupy a space of about 1/2 a millimeter. So we imagine each atom is a qubit, and the qubit levels are stored within the hyperfine levels, in our case, of each atom. As I'll explain in a minute, we operate quantum gates, quantum logic gates, and interactions that allow quantum simulations with optical laser beams, not the ones that cause the atom to glow. Those are measurement laser beams, but when you turn those light beams off, we can turn other dispersive beams on that apply forces. And I want to tell you a little bit about that. And what you should be thinking all along, and I'll address this later, is how on earth are we going to scale this? Okay, 80 is a decent number of qubits, but how about 800? How about 8,000? We need to have a path for that, and we always have to be thinking about that. Okay, so let's get down to the individual atom, atomic physics part of the talk. Okay, this is the reduced energy level diagram of ytterbium-171. And ytterbium-171 has a spin 1/2 nucleus and a single outer valence electron. So it's very much like hydrogen, a very simple atom, surprisingly. The ground state, in fact, the quantum numbers are exactly that of hydrogen. And so we have in the ground S manifold of that electron 4 levels. 2 of them are magnetically insensitive, the M = 0 states. And those are we call those atomic clock states in atomic physics because they're insensitive to magnetic field noise, which we all have in laboratories. So when we write the splitting here, it's about 12.6 gigahertz. I can write it out to 1 hertz here. I could probably write it out even more. And every atom has exactly this same splitting. There is a small quadratic Zeeman shift, but it's small enough that we don't really have to worry about it. And then when we shield the system, we don't really do this in any of our experiments now, but if we were to shield it, we could go another few digits. Okay, so the idle T1 and T2 times of these qubits is essentially infinite. Even the T2 time is infinite because it's defining the second. These are atomic clocks, so you can even sacrifice one of the ions as a sort of a feedback mechanism, and the laser that drives all the others is locked to this atom. And so in that way, we really don't worry about T1 and T2. T1 is like 10,000 years because it's only a microwave splitting. Okay, so that's the qubit. It's a very stable qubit. Sometimes we call it spin up and spin down, especially when thinking about quantum simulations of spin systems, which is what our system really is. Now, I mentioned before that when we measure the state, we have to open the doors to the environment. And this is afforded by coupling to an excited state that does radiate. You'd never store quantum information up here because it only has a lifetime of 10 nanoseconds or so. But due to selection rules, when we apply a laser of a certain color and a certain polarization, this is a little bit simplified, we can scatter light very efficiently, depending on the state of the qubit. So if this qubit is in the state spin up and we apply this light, it's a so-called cycling transition. It goes back and forth, and we can collect. We don't have to collect all the light, just some of that light, and that's a big signal. All atomic ions that are used in and neutral atoms that are used in the field have some type of a transition like this, where we have optical fluorescence. This is real data with a single atom, where we have integrated for about 50 microseconds, and we get about 30 clicks. So we're getting about a photon every microsecond. The atom is scattering a photon every 10 nanoseconds or so. That was the lifetime. So we're only collecting 1% of the light, and we still get a healthy signal. This is a histogram of, I don't know, a few hundred runs. We mostly see about 30, but sometimes 40, sometimes 20. Almost never do we see 0. And that's the point. When we shine that same light on the other quantum state, we pretty much see darkness, because this same laser is now 12 gigahertz away from a 20 megahertz line. So it's many line widths away, and the atom is transparent. We pretty much see nothing. Now, these are histograms over many runs, but in a single shot, we therefore have confidence that we can detect in a single shot with very high fidelity the state of the quantum system. Now, my colleague Jungsang Kim has observed more than 3 nines of state detection efficiency in this hyperfine qubit, actually in a very short amount of time, by using fancy detectors and high NA light collection and so forth. The Innsbruck group has gotten even more nines here. If you store a qubit in a different way, in an optically excited state, you can get many nines. Put it that way. That's not any limitation. It's not close to being limiting in ion trap experiments. So we have I would say we have nearly perfect measurement. And the initialization is afforded through optical pumping. I didn't talk about that, but we typically start every experiment with every atom in the spin down state, or the 0 state, if you want. Now, the interesting optical interaction is the one I said before that allows us to do gates and entanglement. And I want to dwell on that for a few minutes. This is really why ions, why the importance of having a charged atom. So we typically do this by shining 2 laser beams on an atom. And those 2 laser beams are each detuned from the excited state by a lot. So they're highly dispersive. In our case, for ytterbium, the best place to tune for atomic physics reasons, you can argue this if you want, if you look at the details, but it's about a third of the way between these 2 lines, the P1 half and the P3 halves lines. So it's a few tens of terahertz detuned from a 20 megahertz line. So this is really far detuned. It's a million line widths away. So there's very little scatter here. The scatter is 10 to the minus 4, 10 to the minus 5 per cycle here. So you can pretty much, that's in the noise. These 2 beams have a precise beat note. We control that beat note to be about 12.6 gigahertz. And what happens is there's something called a simulated Raman transition. This is a common technique in many optical systems, even in solid state quantum dots and so forth. In chemical systems, molecules, it's a pretty well-known thing, and it's a coherent operation because there's no scattering from the excited state. It's a 2-photon coherent transition, and by precisely tuning the beat note, we can do a coherent operation, make superpositions of qubits. Okay. Now you can also do that with microwaves. If we shine microwaves on the atom, we can also do sort of a single atom NMR if you want. And the reason we don't use microwaves so much, it will become apparent in a minute. The nice thing about these lasers is they have the photons have a lot of momentum, and they will allow us to exert a force on the atom. And I'll get to that in a minute. Now, you might ask, why ytterbium? It's heavy. And to trap a ytterbium, I didn't talk much about ion trapping, but the heavier the ion, the bigger the voltages you have to apply to hold it, in a given motional state. And that's true. But the one great thing about ytterbium is that the fine structure splitting is really big. It's about 100 terahertz. And the optimum wavelength to do this coherent op is at a commodity wavelength. It's at 355 nanometers. And the point here is that, so this is not really physics, this is engineering. These lasers exist. You can buy as much power as you want at 355. So the laser we use for this is actually a pulse laser. It's a mode-locked laser made by Coherent up in Lubeck. We like that model, called the Paladin. It produces several watts of average power. And the whole point here is that it only has one knob, and it's the on knob. You punch it on and it runs for years. That's my kind of laser. It's pulsed, so it produces a frequency comb, and we actually control the spacing of that comb to do all the frequency discrimination. But this laser allows us to run all these coherent operations. And we don't have to spend most of our time in the laser frame, which is what we do in atomic physics often. But the good news is that's really changing. Atomic physics is not what it used to be. So why lasers and not microwaves? Well, because we want to apply a force. The force will allow us to entangle ions that are in a chain like this. So when you see a chain of ions, you should think a bunch of pendulums connected by springs. And so they have an obvious Coulomb interaction. When one of them moves, they all know about it. Think of it that way. The basic idea is if we want to entangle, if we want to run a qubit quantum gate between any two ions, we're going to shine laser light on just those two ions. So we need some pretty fancy optics to be able to address individual spins. And this force, it's called an optical dipole force. And the exotic part of this, it's not super exotic, is that the force depends on the qubit state. So in this picture, if the qubit is in the state up, you can imagine the atom moves up a little bit, only a few nanometers. And if the atom's down, it moves down. And what we're doing here is we're sort of engineering, this is little loose language here, but we're engineering an electric dipole. The atom is a charge, and we're sort of smearing that charge out, sort of like a p orbital in an atom. Okay, so we get an induced dipole. And if we do this to two atoms at the same time, there's going to be a dipole-dipole interaction. Another way to look at it is as long as the displacement is small compared to the separation, so nanometers versus microns, you can consider the Coulomb energy now depends on the internal state. If both atoms are spin up, their Coulomb interaction is exactly the same. If they're spin down, they're both the same. But if they're mixed, up, down, or down, up, they're a little bit further apart. And so the Coulomb energy has a little bit of a defect. And if you expand it to lowest order in delta, it turns out to be a dipole interaction, 1 over r cubed. And the effective dipole moment is the charge times this distance. And that's a big dipole moment, actually. So this is how we couple trapped ion qubits. We have a dipole-dipole interaction. Now, in the language of Boolean logic, in the language of doing an entangling gate, we consider the 4 possibilities of those 2 spins. And as I just told you, down, down, and up, up are left alone. They don't see any change in energy, but the 2 mixed states suffer a little bit of a phase lag. Just, the simplest application of the Schrodinger equation is that you get a phase shift if the energy changes for a certain amount of time. So when we set this phase shift equal to pi over 2, this is a nonlinear gate. It's actually equivalent to a C0 gate. It allows you to have full entanglement if you set phi equal to pi over 2, okay? Now, there's a few, this slide is a little bit back of the envelope, and there are a couple of lies. The first one is, the first one is that, in fact, we apply this spin-dependent force in the x basis, not the z basis of spin. So the x basis means, spin up is down minus up, spin down is down plus up. So the transverse basis of spin. And the native operation here is actually an Ising interaction in the x basis. So it's the effective Hamiltonian is sigma x. And we can tune the angle here. The time it takes in practice for a reasonable laser power is 10 to hundreds of microseconds. So it's not particularly fast. If you're building a computer, the clock speed is not super fast. Of course, this is a quantum computer, so we can get away with anything. The fidelity of this operation, again, it largely depends on just classical noise. The laser, does it have intensity noise? Is there power noise on the laser? Things like this. Is the qubit wandering? That's usually not the case, but they're very high fidelity gates. They probably can be 4 or 5 nines natively. And this type of a icing operation was largely developed by Mulmer and Sorensen, but also concurrently with a few other works. And it's largely based on the Serac-Zoller model. That's a little bit different. The Serac-Zoller model is not practical. Nobody uses it because it's a little more demanding. But the physics, the central physics is there, that we're modulating the Coulomb interaction to do this. The other I don't want to say lie. The other detail that I didn't talk about is when you poke just 2 atoms, what about all the other atoms? They're all going to move around, and that's absolutely true. And so, in fact, I'm not going to talk about this very much, but in fact, this is a classical control problem, because I think it's sort of like plucking 2 parts on a guitar string. If you pluck them in just the right way, after the entanglement's over, you can make sure the guitar string returns to its undisturbed state. In other words, we're not entangling the spins with all the phonons, the quantized vibrations. We know how to engineer the laser pulses to get rid of that. And it's a classical scaling issue. As we add ions to the chain, we're adding a little bit of classical complexity, but not too much, as it turns out. And that doesn't limit the fidelity. Okay, I could give a whole seminar on that, the laser control there. But again, we like to toss, in ion trap quantum computing, we like to toss as much as we can up the stack to classical control, because we're confident that we can solve that problem. The quantum is all done. It's the atom. We don't manufacture them, and we're not asking for anything exotic in terms of the quantum. It's all about classical control here. So here's a little animation of how these gates work. So we might execute a quantum circuit here. In a typical space-time diagram. So 7 qubits vertically, and time goes left to right. The first thing we do is optically pump the atoms to their spin down or 0 state. And then we apply a bunch of gates, which are just pairs or single laser beams that hit target atoms that are involved in the gate. You can do things in parallel. I'm not talking much about that. We can hit them all with lasers at the same time if you want, and have an all-to-all icing interaction. These single boxes are single qubit rotations. Those are usually pretty easy. And then the dual ones, you can see the atoms are kind of fuzzed out. And then at the end of the day, we measure. And this is maybe the best part of ions, is that when you measure, it's just a very clear signal. The atoms that glow are 1s, and the atoms that are dark are 0s. Okay, so that's basically how a trapped ion quantum computer is going to work. Now, I mentioned that trapped ions are among the most highly performing quantum systems out there. This data, all these points here, which represent the entangling gate errors or fidelities, these are just complementary variables, over the last 20, 25 years or so in 3 different technologies. You can see, everybody's getting good at all of their technologies. So take this plot with a grain of salt, because pretty much every one of these data points involves exactly 2 qubits and no more. And indeed, trapped ions are coming down fast. Superconductors came on the scene, 15 or 20 years ago, and they learned how to control their system. It's a little bit worrisome that it looks very hard at scale for superconductors to do better than 99%, but we'll see. There could be breakthroughs in materials that'll allow that to go, but we'll see. Neutral atoms have been coming on strong lately, not in terms of individual control, but more for simulators. But they're also very clean for many of the reasons that trapped ions are clean. The one big difference, I think, is that trapped ions are held. They're confined based on their charge, and that does not in any way disturb the qubit. Whereas neutral atoms, you don't have a charge, and so they have to be distorted in order to trap them. And that means that the trapping itself can add noise to the qubit. So when you get to scale, that's a tricky thing. Okay, now getting into the lab, if you've seen an atomic physics lab, it looks something like this. This is from several years ago, one of our ion trap labs, and it's sort of a mess. And I think it's no surprise that the companies that wanted to build quantum computers, they started with solid state systems, superconducting systems, because they were very nervous about this. This doesn't look like you can scale it. And in fact, the chambers here, you can barely see them. They only hold a few ions. It's all the infrastructure, which is optics and electronics, FPGAs, and so forth. The good news is we know how to, this is a physics lab. And if you want to build something and engineer it well, you don't need or want flexibility on every single mount. So over the last few years, we've, without too much exaggeration, we've shoved all of this stuff into a box. And this is a picture of that box. It's not empty at all. It has, again, without much exaggeration, it has almost all of this stuff in there, all of the optics anyway. There are a few CW lasers that are fed in by fiber, but the laser that does the gate work, the coherent laser, it's in there, the vacuum chamber, the ion trap chip. And we were afforded the ability to do this mainly through a project funded by IARPA, the U.S. Intelligence Research Agency, and also the NSF STAC program. And these programs allowed us to, I know there's performers in the same IARPA program at ETH on the superconducting side. But these programs allowed us to fold in industrial suppliers, Sandia making the ion trap chip, L3 Harris, coherent AOSense and cold quantum making optical systems, cold quantum making vacuum chambers. So, working with industry is expensive. And so it was a little odd for a university outfit to be able to field a device like this that's been so well engineered. So when you look inside this box, what does it look like? Well, the high-level schematic is just a bunch of atoms, and we have counterpropagating Raman beams to do these two photon transitions. I forgot to mention they have to be counterpropagating, or they can't be co-propagating. Otherwise, if they're co-propagating, there's no force. So what we do is we have a big fat beam from one side and a bunch of individually addressing beams from the other side. And sort of the neat device in this system is a 32-channel modulator. We split the laser beam into 32 beams, and we can turn on and off every one of them. Not only can we turn them on and off, we can phase, frequency, or amplitude modulate them at will. And so there's a lot of, this is the classical control I talked about. Remember, plucking the guitar string just right. It becomes an RF problem. And so we have some fast electronics, the brains that interpret a circuit and come up with laser pulses that program each of these individual channels. So we have 32 individual cables. You don't see them, they're behind here. 32 cables that send the signals that tell us what to do. And then there are other signals that say measure the qubits or initialize the qubits. And there's all kinds of other stabilization, active stabilization going on in here. We don't open this box, but once every, 3 to 6 months. We've only opened it a few times since we closed it in late 1999. Okay, so what we realized in building this system is that we stopped doing atomic physics. Well, we're always doing atomic physics, but with a very stable system like this, we can start to consider other things like, this middle part of what we call the quantum stack. The atomic physics is down here. At the high level, you have a theorist or somebody that knows nothing about quantum, but is running algorithms, so somebody at a very high level. In between, we have the conversion from high level to low level. So there's gate compilers, there's these pulse shapers I mentioned in the laser beams. So this is really the black art of what we've been doing the last few years. And it's kind of interesting. I've spent my entire career down here, not really looking up at all. And in the last few years, I found that I have to learn I have to learn other areas of physics like cosmology. I'll show a very brief application of that in quantum computing, but also control systems, FPGA devices, and so forth. So the field is really broadening, and it's not just not atomic physics. It's not physics anymore. It's much more. So that's pretty fun. So we started several years ago, starting to form lots of collaborations. Some of these are quantum simulators, some of them are quantum computations, and just all kinds of collaborators coming out of the woodworks that want to run some application or some physics problem on our system. And the year 2020 was very busy, and a lot of this stuff's still in progress. I should probably update this list. more publications on the way. And I'll note that on my team from a few years ago, we had Norbert Linke and more recently Marco Cetina and Crystal Knoll. All three of them are now faculty members at Duke. And also, I'll mention Guido Pagano, who just moved to Rice about a year and a half ago. So I want to talk about a couple of these. I mentioned, I think Cornelius mentioned the interest in using these things to simulate magnetism. Well, this is, I apologize, this is a couple of years old, but it's one of the bigger experiments we've done with spins, and it involves measuring an interesting phase transition, well, what's known as a dynamical phase transition, which is strange because a phase transition presumes a phase, which presumes equilibrium, but this is a non-equilibrium phase transition, if you will. And so what we're doing here is a so-called quench experiment. What that means is that we expose the ions to a long-range icing interaction, but we're not near the ground state of that icing interaction. So the reason is this experiment, we prepare all the spins along the x-axis. So that's up plus down with a well-known phase. So it's up plus down, all of the spins. And then we turn on this Hamiltonian. What is it? Well, we turn on all the beams. So all of the ions are exposed. We in fact do this with a big fat laser beam. It's very easy. We don't even need to individually address. So we have a big laser beam, and it turns out the icing interaction is long range. I mentioned before that in a certain limit, we expect a dipole-dipole coupling, 1 over r cubed. But if you couple to all the normal modes near resonance, you can control that exponent. It's not 1 over r cubed. It can be 1 over r. It can be 1 over r to the 0 power in certain cases. And so we have a very long-range icing interaction, and we can control. This is an interesting knob. We can control the exponent in the interaction range. And we can add a transverse effective magnetic field. This we can get by, this could be a real magnetic field that shifts the qubits, but in practice, they're AC Stark shifts from our laser beams. Won't get into that. But these two parts of the Hamiltonian don't commute, and they will compete with each other. If you prepare the spins along X, they're all going to precess around this magnetic field, but they also want to order according to the pattern and the signs of these couplings. So there's this competition between precessing around the Z-axis of all these spins and ordering along X. Now, if they're prepared along, if B is equal to 0 and they're prepared along X, nothing happens because they're already in an eigenstate of Hamiltonian. It's not this ground state, depending on what J is, what the sign of J is. But as soon as we add a magnetic field, there's this competition. If B is really big, then we expect fast dynamics around the Z field. And if B is really small, we expect them to order along the X-axis. And then we simply measure the spins along the X-axis. We do this by unpreparing the spins along X. It's sort of the reverse of step 1, and then we measure. So if we look at a simple observable here, and this is, I think, this is with I think 12 or 15 spins. If we measure the brightness of the chain, that's the total magnetization along X, we see as a function of B over J, for low B over J, we don't see much going on because we're already in an eigenstate of X. But as we turn up B over J, you can see we start to see that precession around Z. There's clearly different kind of dynamics going on here, but I wouldn't call that a phase transition. It's just sort of a smooth, crossover, if you want. Well, let's measure correlation functions now. Here we're measuring the average of all 2 spin correlations. And remember, we measure in a single shot every single spin, so we can form any correlator we want. So here we plot this correlator as a function of B over J for different numbers of spins. And so at very low B, they're already correlated, and at very high B, we see a revival of the correlation. And as the number of spins grows, this dip gets a little more pronounced, but again, nothing to write home about. The dashed line here is mean field theory. So you can see that kind of in this, when B is around J or bigger, then, we have lots of entanglement going on, and we can't calculate things based on simple mean field. It's a long range interaction here. In the infinite spin limit, we expect a logarithmic divergence here, which would be a true, a big singularity, but we hardly see that even up to 53 spins. As I said, we can measure every correlation function. So let's take a snapshot of the whole crystal and measure an n-body correlator. And in this case, we measured in any single shot, we looked at the largest domain, that is the largest size block where all the spins are in the same state. And we average that observable over many runs, and then we change B over J. And we see, as you can see, the data over here, there's a minimum in the average domain sign. It is pretty sharp. That's pretty sharp. And the dashed lines are just a guide to the eye. The point to take home here is that we couldn't calculate exactly where this crossing is. It's at about 0.96, I think. You're tempted to say it's 1. It's actually not exactly 1. And we can't calculate that because there are too many spins, 53. 2 to the 53 is a big Hilbert space. And by the way, this was well before the Google quantum supremacy experiment. And it's funny, they also used 53. It's a funny number there. Now, more recently, we've used a similar system to study all kinds of other quantum simulations. One of an analog to asymptotic confinement based on this long-range icing interaction. We can create little domain walls and watch them be confined, and we're also studying how they bounce off each other now. I'm not going to talk today about time crystals, but it's a very similar type experiment where we were able to stabilize the dynamics and show that it's insensitive to perturbations in a way that has this cool name, time crystal. And you can type it in Google and read about that. Also studying how this system doesn't thermalize. There's something called many-body localization. Time crystallization is an example of that as well. And so it's been very interesting, learning new physics, in this case, more condensed matter physics, but also the idea of thermalization and what it means in a quantum system. I'm going to quickly go through this. This is, again, an old one. This is a quantum circuit that has interests in the field of cosmology and black holes, believe it or not. And the idea here is that there's a property of quantum unitaries called scrambling, which you may have heard of, and it's more than just entanglement. Scrambling means that you have infinite depth entanglement. In other words, the system is entangled at all depths. And it's relevant to black holes because black holes are thought to quickly scramble any information, or if you throw a qubit into a black hole, it gets scrambled with all of the matter in that black hole. So to detect whether a unitary scrambles or not, though, is tricky. And in this circuit, basically, it's a very small circuit. We're dealing with only 3 qubits, unitaries, 3-qubit unitaries. And this circuit is a litmus test for whether the unitary U scrambles or not. And so U can be anything. It's only a 3-qubit circuit, so we made a very general circuit where we can tune what we expect to be scrambling and not. And the reason you need 3 qubits is that with only 2 qubits, you have entanglement or not, and there's not much depth. So if you're entangled, you're also scrambled. But with 3 qubits, there are states that are entangled, but not that. There are unitaries that entangle but don't scramble. So you can see in the circuit, we need to apply U, and we need to apply its inverse. And this but by doing this and initializing the system, we have an unknown qubit in the first rail, and we have entanglement, EPR entanglement across pairs based on a Bell measurement in any one of these 3 Bell detectors. It turns out if and only if U scrambles will we find this state, this unknown state, appear on the last rail. So it's actually a teleportation from a protocol from one qubit to another, but it only teleports successfully based on measurements of Bell pairs if U scrambles or not. And so this is you might say this is a three qubit black hole. That's a little bit goofy, obviously. And to scale to real black holes is obviously out of the question, but understanding the behavior of black holes and even up to maybe 20 qubits, there might be some interesting things there. And Lenny Susskind at Stanford has been very excited about this. This is, by the way, a collaboration with Norm Yao and at Berkeley and Benny Yoshida at Perimeter. So here's a picture of a real black hole, a couple of them, and a wormhole in between them. And I'm told, I don't quite understand this. I'm told that an analogy that wormholes can be compared to what entanglement allows you to do between black holes. It's a very deep thing that, again, we're all students here, but Lenny and others, John Preskill and so forth, they've made that connection, and it's very profound to me. And I think what's at a high level, what's interesting is that we're using these small quantum computers to maybe say something of interest in cosmology. Okay, now changing gears back to quantum computing. I didn't talk at all about error correction, but as you know, qubits and their gates are sensitive, very sensitive to errors, very much like analog computers. And the ability to do quantum error correction was, I think it was an advent that came shortly after Shor's algorithm in the 90s. And to get more nines on your gates, at some point, we're going to have to turn to error correction. With trapped ions, we don't need error correction until we get, I think, probably beyond 3 nines, 99.9% or something like that. But if you want to do 1 million operations, you need 6 nines on your gates. So to do 1 million operations, you're going to have to do error correction. So many in the community are starting to encode qubits into error correcting blocks. This 13-to-1 code, it's actually a 9-to-1 code called the Bacon-Shor code, where we get 1 logical qubit out of 9 physical qubits. We need 4 extras in order to do the feedback. In our experiment, we didn't quite do that feedback because we need partial measurement. We need to measure those 4 and then feed back to the other 9. We're on our way toward doing that, but we did the encoding, the unencoding, and the measurement of all the stabilizers. And again, we indeed showed that the qubit that we encode is much less sensitive to errors, and we even did single logical operations on that qubit. Again, this publication describes that, and we're working hard on the partial measurement capability in our system, which is well on its way. So this is the IARPA program. It's called Logical Qubits, and this was the whole point, to identify a good code and implement it. And what's noteworthy here is that the threshold for when this can be useful is at 99.9%. If you have a 99.9% gate, you can start using this to get more nines. And the overhead, 13-to-1 is not so bad. It's worse than classical error correction, but 13-to-1 for quantum error correction is damn good. Now, it doesn't get you infinitely many nines, but it can get you another 9. It's like buying another 9 by using an overhead of 13-to-1. And that's going to make a huge difference in coming years. Again, you shouldn't use error correction until you need to. And right now, like in this earlier experiment here, we didn't need any error correction because we only had 7 qubits, maybe 50 gates. So we didn't need error correction. We'd be silly if we'd used it. So yeah, the point here is that with ions, because the native error rates are so low, we don't need so much overhead. More recently, we've been implementing protocols to compare different quantum computers. And this is based on theory by Peter Zoller and his group, and this is a collaboration with Mohammed Hafezi. The idea here is if you have 2 quantum computers, the best way to test them is to coherently have them interact and sort of do full tomography between them. That's, of course, very hard because full tomography it scales exponentially with the size, way too many measurements, but also it's rare that you can get a coherent channel between, say, a superconducting quantum computer and an ion-trapped quantum computer. Okay, so Peter and his group showed ways that to compare quantum computers without having to do that at all. And the trick here is that you sample from a randomized selection of measurements following a standard operation on both quantum computers, V. And on both quantum computers, you make the same random measurements. That is measurements in the same random bases between the systems. And by taking lots and lots of data, you can compare them. So what it allows you to do is not have to have a quantum channel between the systems. It still takes exponential resources, though. But as Peter likes to say, it's a kinder exponential. So we know full-blooded tomography, even on a single quantum computer, pretty much peters out at, 12 to 20 qubits. But with this technique, we can maybe get beyond 30 qubits, maybe 35 qubits. And this is data, right. So you can look at this archive by Daiwei Zhu et al. But the data basically is a comparison between 3 IBM superconducting systems, 2 University of Maryland systems, and an IonQ system. And the simulation row here denotes what we expect a given quantum state to be. By the way, this is for, I think, a 7-particle GHZ state. But in this paper, we made several different target quantum operations, and we wanted to see how they compared between the systems. And what was interesting, you have to kind of stare at this table here. What was interesting is that the ion traps, the 3 ion traps, sort of they compared well to each other, but not very well to the superconductors, but the superconductors compared well to each other as well. So it's an interesting case where we have different technologies having a type of a systematic error that we don't quite understand. But anyway, we found that kind of an interesting protocol to compare different systems, even in different states. No reason we can't do it between different countries either. Okay. So very recently, we've used our circuit machine to measure phase transitions based on random measurements inserted in a coherent circuit. And because we don't have mid-cycle measurement yet, what we've done here, our measurements are, we use a set of ancilla qubits to effectively do the measurements, and we do it at the end of the day. And then in the office, we can say what circuit we used. And again, this is a collaboration with David Hughes and Michael Goulans. And basically, this is sort of like a percolation phase transition. And as we vary the measurement density, we can see that the entanglement entropy of the output state, obviously goes down as we increase the measurement density. And as we add qubits to the system, we can sort of see this maybe crossover. It's more than a crossover. We say there's no flow here, and we can identify a critical measurement density where we see this phase transition. And again, there's an archive paper if you're interested, you can look there. Along the topic of quantum computer verification, we've actually ran a few different algorithms that allow us to certify a quantum computation classically without needing a quantum computer. So, for instance, the Google quantum supremacy experiment, you require a quantum computer to verify it, because when it gets too big, a classical computer fails. But something like Shor's algorithm, right? If I give you a bunch of big numbers and you can factor them every time, I must conclude that you have a quantum computer, unless factoring is easy. Well, it turns out factoring is very hard, as we know, but there are easier problems in factoring. This is one of them. It looks like Shor's algorithm. It's not x to the a mod n, but we compute x squared mod n in a circuit machine. This is a 2-to-1 function. That is two inputs x collide to give the same output. But you can't, even if you know one of the inputs, it's very hard to find the other input unless you can factor n. So it's a little like Shor. And we implemented this algorithm with up to, I think, 15 qubits. And indeed, this paper should be out in the archive very soon. We have indeed showed that we can, with the quantum system, we don't compute the colliding pair, but we can show whether their parities are the same or different. And classically, you can't do that. This was with Norm Yao and Umesh Vazirani. The second circuit, which has a similar endpoint, was a collaboration with Thomas Vidic at Caltech. And this is a learning with errors model where we have matrix multiplication, but we add, we're adding an error that's hidden. And the question is, can we find this hidden vector S if we're clouded by this error? And I won't get into the details. It's a pretty deep circuit for having about 10 qubits. And again, it's a sort of a one-way function. We can compute this, but it's hard to go back. So I want to start to conclude and talk about scaling. We've done all these, many applications with a few qubits, but how are we going to scale? Well, the good news with trapped ions is that we have a very concrete scaling architectures, and one of them is sometimes called the QCCD architecture. And by the way, I borrowed this slide from IonQ, and they're obviously busy scaling. And the idea here is this ion trap chip. Here you can see all the electrodes. The ions are trapped above this middle surface here, and we've trapped 4 chains of 16 ions, and they're separated. And the idea is to have these. This is sort of a multi-core architecture, and then this is a real picture in blue of 64 ions, and we're bringing 16 plus 16, and then we're moving to the next 16 plus 16. And the whole point here is that we can move these 16 qubit cores together and then do local computations and then separate and continue scaling without adding ions to a single crystal. Now this animation here, the video is real, but we haven't done any quantum computations in this system, partly because we need multi-species ions to do sympathetic cooling, and these are all one species for now. But the point is we know how to control the waveforms on these electrodes to move the ions at will and do what we want. And so this is a well-known architecture that was first pointed out by Dave Wineland and myself almost 20 years ago, and it's being used by many groups. This article here, I should have also cited the Honeywell team, which has really pushed this more than anybody on the ability to shuttle ions around and do gates. So that's scaling strategy 1. And the point is you don't need to do this unless you have more than about 20 qubits. And we're sort of there. We're busting out more than 20. But if you only have 10 qubits, you don't need to do this. And so I think, I don't know, one thing I've learned over the years is don't do something if you don't have to do it. But the point is we sort of have this architecture ready to go. Now, the second scaling architecture will be further out when we need to go to thousands of qubits. And in this case, we're going to map ion qubits through photons and then have those photons interfere. And there's a heralded way where we can announce that a couple of qubits are entangled based on photonic interactions. This architecture, we demonstrated the first ingredients of it over almost 15 years ago now. And it's now being used in many different optical platforms, but also microwaves. Now, what's really interesting about this scaling architecture is that it is fully connected. We already have full connections within a single crystal, but this architecture is fully connected at scale because we have this N by N cross-connect switch, an optical cross-connect switch. We can interfere photons from any one of these fibers. So the graph is interesting. It's sort of this hierarchical, fully connected graph where we have a bunch of clusters of ions that interact via the Coulomb interaction. And then based on the configuration of the switch, we can interact between any pair of red qubits here. So there's no other quantum computing architecture that has full connectivities at scale. And this is not really important now when you have 10 qubits. It's going to be hugely important when you have 1 million qubits. You better have very good connections for error correction and for any kind of expression of an interesting algorithm. So we have that with trapped ions. So looking a little deeper into the physics of this connection, the idea here is these trapped ions, they might be far apart, different chambers on different chips. What we're doing here is we're causing them to emit photons, single photons. And that might sound exotic, but we have single atoms. If you have single atoms, it's easy to get single photons. And when you collect those photons, they interfere and they can herald entanglement between the spins. And the reason is the photons, when they're emitted, the polarization or the time delay, something in the photon is entangled with the atom. And we can do that with trapped ions. And when we detect certain coincidence events on 2 photodetectors after a beam splitter, that sort of erases the which path information. So if we get certain coincidence events, we can herald, we can know for sure that the atoms, the memories are entangled, either in a singlet or a triplet form, depending on what detector's fired. And so the rate of this entanglement is the hard part. This is the problem. It's very slow. It scales like 1/2 because we only get 1/2 of the possible states. Looks like, looks like I'm have missed the state here, but anyway, we don't get the other two states. So we only get 1/2. We have a rate at which we're trying to repeat this. It's a repeat until success. And the probability of success is p squared, where p is the probability that we captured a single photon and got it through the fiber. And p is, it could be 1% or something, a few percent. So p squared is really small. Now, the state of the art is a couple of percent. And if you repeat at a megahertz, you get something like a few hundred events per second. And this is work from Oxford, David Lucas's group, Chris Balance et al. That bested our result by more than an order of magnitude that were a few years earlier. When we first demonstrated this protocol in 2007, the rate was 0.001 per second. So we've gained 5 orders of magnitude in 10 years, and we do think we can stretch it to the few thousand to 10,000 events per second. And it's not synchronous, but we can make it synchronous as well by using a first in, first out buffer architecture. And the beauty of this photonic interconnect, I should say that this has been reproduced in almost all the platforms that are optically active, but even superconductors. And one experiment actually at ETH in Andreas Walleroff's group to interfere microwave photons in this way. The beauty of this type of scaling is that it'll involve technology that has not yet been put into play. So this is all classical technology. Most of it exists now. Think about a data center, wiring quantum computers like a data center and integrating optics on the chip. A lot of that work is already, it's been going on at Sandia, and also, Jonathan Holmes' group at ETH and MIT Lincoln Labs had concurrent papers on this integrating optics with ion traps just in the last year. This is my colleague Jungsang Kim standing next to the world's largest N-by-N optical switch. He built it at Bell Labs some time ago. So I'm running out of time. I want to just sort of conclude by noting that the ion trap system, I would also not want to think this could scale, but in fact, it's probably the only system that can scale because it's going to get smaller. It's going to get smaller over time. We're already seeing that. I didn't talk much about this vacuum chamber here. It's sealed right on the chip. So this is a very small system. All of the guts are right here and everything else is just optics. And we know that lots of engineering efforts are going to help that. This is a picture from Lincoln Labs where they have integrated some of the optical functionality on the chip itself. We look forward to that in the future. And then this is sort of the data center view of how we can scale to thousands or millions of qubits. And this is, of course, what the company IonQ is all about. We're building these things, and with the full confidence that we will scale them because we have these technologies to bear, will allow us to do that. And really great news from IonQ is that we're going to be a public company in about a week or two, and we have a big market capitalization. This will allow us to go in these directions and hire the engineers to make these systems work. And I think with that, I wanted to just show, I'll talk more about IonQ tomorrow, but I do want to mention just one more quick slide. And that is, we certainly in trapped ions, we see a challenge here that it's very hard to build a system, like your iPhone, that people can use without knowing or caring what's inside. But that's what we have to have in a quantum computer. It's very hard to do that at a university because we don't build kind of commoditized things. That's what industry does, but industry is not yet, I think the seasoned engineers look at this technology and they don't know what to think about it. So there's a little bit of a disconnect there. And I think we're in a time now where there are national labs and big user facilities that can be put to bear. The national labs, at least in the US, don't have that much history in the field outside of NIST, but like the Department of Energy labs, the Department of Defense labs are shouldering a lot of this in the US, and there's a little bit of a challenge there. And finally at Duke, we're standing up a user facility that we will build these systems for science. And it's important that they be used for science because the commercial use of quantum computers is still a few years away. And I think it might be, you could argue that the scientific uses will ensure that we get there. And we have a huge ion trap bench, 7 ion trap experimentalists at Duke and some theoretical firepower. And we're just getting going at the Duke Quantum Center. So thank you for your attention. Happy to answer any questions.
Thank you very much, Chris, for this very exciting and very comprehensive talk covering both the introduction into how we do trapped ions and lots of highlights and experiments and also an outlook at the end. So this was very well done. So thank you very much. The downside of being virtual, I can clap like this, and I think lots of other people I can see are clapping online as well. And I think we do have a little bit of time for questions at this point. So I'm just opening the floor now to questions. So I think because there are a decent number of people, but yeah, if you have a question, please unmute yourself and just fire away. And if not, I'll have one or two. I see there's a raised hand. G.
Oh, hey. In your Raman scheme, you have a global beam addressing all the ions. I'm wondering whether that is causing AC dark shifts to those idle ions, which are not coupled by the individual addressing beam. Do you need to compensate or keep track of this AC dark shift in your computation sequence?
So you're asking about the Raman beams and start shifts because the global beam is on all the time?
Yes, that's right. Yeah.
Yeah. Yeah, very good. Very good point. Now, it turns out by using clock states that have no Zeeman shift, it turns out the direct Stark shifts are also very small. But there are higher order Stark shifts because, as you might know, you probably know based on your question, that the gates, we apply detuned laser beams. So there's actually we call it a 4-photon Stark shift. And those can be significant. Fortunately, we know what they are. And as long as the intensity of the laser is stable, as long as we know what we are, we have to calibrate them. But you're right. Those are important. We need to know what they are. Yeah, good question.
I see. Thanks.
I see there's another question by Chris Galland. Please go ahead.
Yeah, okay. Thank you so much. It was a very inspiring talk. I would like to ask about your roadmap for the next few years, because you showed many things to scale up. And do you know, for example, how many qubits will have the next device, and will it be through interconnects or just by putting more ions on the same chips? And what of many steps ahead do you already see in the future?
Well, okay, so IonQ is going to scale much faster. They have a lot more resources to go, but at the university we are we can afford to take more risks on the research side. So both at IonQ and at universities, we're integrating these ion trap chips with photonic connections in order to go in that direction. But that, I think, before we get integrated optics, that you saw the gate times with photonics is about, I don't know, it's maybe 100 times slower than the typical Coulomb gate. Yeah, it's not too bad as long as you don't use the photonic connection, but more than 1% of the total time, you're probably okay. But we want to use it more than that. And so, there's a lot of research on how to collect light more efficiently. I think many groups are looking in this direction, including at ETH and in Innsbruck and NIST and Lincoln Labs.
But can you couple the ions so close, like in the evanescent field of a waveguide, or it's not even possible?
Yeah, that's tricky. The problem, okay, so I've been selling ions as being, just like the best thing since sliced bread. The problem with ions, of course, is that if you can't, what you learn in ion traps grade school is that you don't put any dielectrics near the ion, because dielectrics charge, and uncontrolled charge causes the ions to move around. Of course, the best optics are dielectrics, like surrounding the ion with a cavity where you can collect all the light. And that's really challenging. I think in the future we'll get there, but that's a pretty tricky one. But even passively, we have an experiment at the university where we're collecting with a numerical aperture of 0.8 into an A-sphere, a very high quality fused silica aspherical optic. So it's not a cavity, and it's 6 millimeters away. So it's far enough away that it doesn't disturb. But that's the photonic side. But you asked a really good question. How many qubits can we put in a single chain? I'm going to say that number is between 20 and 100. It's certainly more than 20 because we're doing that now. We've done some experiments with 30, some with 50 even. But clearly what happens is the modes, there are too many modes and they get soft and you get very low frequencies and you have to worry about that. So if you say stop at 50, this shuttling idea, we're starting to do that. When you have a chip trap, you have, kind of for free, you get to shuttle ions around, and we're starting to work on that. And the technology, the tricky part is that you need to do sympathetic cooling with another species ion, because when you laser cool an ion, the scattered light from that ion or from the laser itself can wash out other qubits. But if you have a different species, then you're good to go. They're totally different spectral absorptions. The problem with different species, they have different masses, and the collective motion with different masses is tricky. There are ideas to actually shelve, in a single atom, you can have two flavors of qubits that are disjointed. And what you can do is sort of optically make this a cooling ion, make this a qubit ion. There's some cool ideas coming out of Oregon and UCLA. Some ion trap groups, Wes Campbell and David Alcock are really thinking about this. That's very cool. So it's almost like, again, we're throwing it up in the software stack. Let's make that one a coolant ion and that one a qubit ion. So these, there's so many things to do in these trapped ion systems, and there's so many groups doing it. It's very exciting. I'm very confident that we're going to have many hundreds of qubits to do, tens of thousands of operations in the coming few years.
Great. Thanks.
We haven't needed to do it yet. And that's, some people say, well, how come you don't have 1 million qubits? Because we don't have 10 to the minus 12 errors yet. If you have 1 million qubits, you better have 10 to the minus 12 errors.
See, there's another question by Andreas. Go ahead.
Hi, Chris. Very nice talk. I was wondering what you think is the best approach in ions to do this in-sequence measurements as you require them for quantum error correction?
In sequence?
Yeah, like within a cycle, say within a correction cycle. You mentioned it was one of the bigger
sort of mid-cycle
challenges to measure your ancilla qubits or your helper qubits.
I should have shown some data. We're actually at the university, we're doing it with different isotopes of ytterbium. So it's sort of like the sympathetic cooling. We have ytterbium-171 as our qubit, but we have ytterbium-172 nearby. And so what we can do is, by shuttling the ions away from the zone where we do the computation, we can then read them out, just the ions we want to read out, and then we can bring them back in. And by having the different isotope, we can sympathetically cool to bring them back in. So we're doing this mid-cycle measurement. Honeywell has been doing mid-cycle measurement for some time now. It's pretty much the same idea. They do all this shuttling. Their architecture is based on shuttling. So if you have shuttling already working with multiple species, I think they're using ytterbium and barium. Once you have that, the mid-cycle measurement sort of comes for free. You do have to make sure that when you return the ions, they are right back where they used to be. There's a phase issue with that. So there's some engineering involved. But again, it seems pretty straightforward, and we're starting to do that at the university for this mid-cycle measurement. Haven't done it yet.
So shuttling will be essential, you're saying. Shuttling and use of different species, maybe.
And unfortunately, if you shuttle, you have to have two species to recool, because when you shuttle, it's just too disturbing, too perturbative to bring them back without having them have all this motion.
All right, thanks a lot.
Yep.
Okay, maybe then I'll jump in with a question that is just burning when I look at all the collaborations that you have or have had in the last year alone. So one thing that always makes me wonder is, when I talk to people and they ask about when will there be a quantum advantage? When will we learn something with a trapped ion or with a quantum simulator that we can't learn in any other way? So what's the notion that you've been getting from people now that these systems are available and that they can actually play with them and do all kinds of cool physics? Are we getting closer to this point where we will get a qualitative answer at least?
Oh yeah, I don't know how to answer that question. I guess I'm sort of amazed at the patience of the community. I mean, this dynamic's kind of interesting. We'll typically get approached by somebody, typically a theorist, that knows nothing about atomic physics, which is fine, but they know something about a magnetic phase transition or something like that. And after 6 months of going back and forth, we say, okay, show us the circuit, or show us the protocol. What is it? And then they'll show it to us. We'll say, no, we can't do that. It's too big, and we don't have this. So it can take up to a year before we even consider kind of testing it. And by that time, we're down to some baby system, and they still seem to be interested. So sometimes I'm afraid they're just going to walk away because, okay, we can only do it with 8 qubits. So I'm not answering your question. I think we do need this healthy dose of engineering. And where's it going to happen? From everybody. You know, that's, I mean, I think, you know, 30 years ago when I got started in this field, there were no university groups really doing this, none. There were some national labs, there were clock labs, and now there's, I don't know, several dozen, maybe 2 dozen, you know, very active university groups and government labs, and they're all, you know, putting the pieces together. And I know it's just a matter of time, and I'm thinking under 5 years that we're going to be routinely doing things that we can't calculate otherwise. And so you might argue, well, you shouldn't believe those experiments, but that's fine. That's a good place to be, you know, where we're really breaking new ground. And I really do look. I know I'm being a little. I sound a little hypey here. I don't really see any other architecture getting there.
Okay. Well, thanks, Chris. And it's good to hear that no one walked away yet. So it makes me look forward to more collaborations with future users.
Yeah,
but that's good. Well, if there are no more questions, I think this is a great place where we can wrap things up. And let me also point out that tomorrow the Quantum Center will host its flagship forum, where Chris is also speaking and tell us a little bit more about IonQ. We're live streaming this. It's also an in-person event, but there's a live stream as well. Check out qc.ethz.ch if you want to find the link. So with that, yeah, thank you, Chris, very much for joining us today and presenting what's the state of the art right now in ion trapping. And thank you everyone else also for joining.
Thanks for having me. Bye-bye.
Bye everyone.